An interesting but challenging question on zigzag lines in circles here. My main bit of advice is to say, like, whenever you're using a circle, you're going to have to use the radius. The radius is going to be useful somehow. Now, the first thing I'm going to do in this question is continue the zigzag lines and just finish it off. It doesn't seem any harm in doing that. And then all of these angles that I'm indicating have got to be alpha. But the result of this is that this triangle on the right must be the same as the triangle on the left for it to go down in exactly the same place. There must be a line of symmetry, because if you think about it, if you start from the right and go at the same angle, it's got to meet in the same place at the top, and it's got to come down, if this is alpha, and meet basically the same distance away here. And you can make the same argument here, so there's got to be a line of symmetry going on here. Now, it might be tempting, and actually it was for me, to start like drawing all sorts of kind of, things like this in and so on. But actually, the main point is that there's no real extra information on the right. We could even draw the circle at the bottom and do a similar sort of thing. So I'm going to ignore this completely from now on and just focus on the quarter circle on the left. And then I'm going to take that bit of advice that I gave, which was focus on the radius. And we can see we've got the radius here and here. But what about if I add it here? That's going to be useful, actually. We'll come back to that in a second. So I've got this bigger triangle here, and it's isosceles because the two angles are equal. And in there, actually, they're both the radius then, actually. They must be, because this one is the radius. And then this line here is also the radius, which means the one I've drawn in is also the radius. So all of these lines are equal. And what that will mean is if I draw this one in, well, this here has got to be alpha, and this is going to be 180 minus 2 alpha, and that's also going to be 180 minus 2 alpha. I'm just going to add that on. But if I label the triangles, I'm going to call this A, this B, this can be C and D. What we have is that triangle ABD must be congruent to triangle BCD because they have the same base angles, they must do, and they're going to have the same top angle, and they share the longest side of the radius. So angle side angle gives you congruency. Um, what else is there? Okay, this green angle here must also be 180 minus 2 alpha, because it's just angles in a triangle are up to 180. And therefore, I can work out this angle here, because the whole angle's alpha. So I just need to think, what do I add on to 180 minus 2 alpha to give alpha? And it's going to be 3 alpha minus 180. All right, that's good. So what to do next? Well, actually, at this point, it takes a bit of time to see it, but let's just focus on this triangle that I'm outlining in purple. Note that this length here that I'm now indicating is the base of the bigger isosceles triangle, but it's also the base of ADP, which is congruent. That's why we need to use the idea of congruency. So these two, going to do a double dash, are the same. But then with the smaller triangle, this length here is the same as that other length, so they are also the same. And what I'm trying to argue is that this triangle that I'm now highlighting is also an isosceles triangle. And that means that the base angles 3 alpha minus 180 must equal one another, and the other one is 180 minus 2 alpha. And finally, after all of this effort, I've got myself an equation involving alpha. I can add 2 alpha to both sides and add 180 to both sides, so 5 alpha is 360. Then divide by 5. Divide by 5 effectively by dividing by 10 to give 36 and times by 2. Alpha is 72 degrees. Well done.